we're looking at modular arithmetic, how to do our arithmetic, addition, subtraction and other operations, but everything's mod n. And we've gone through a number of examples. Last lecture we looked at multiplication. Multiplication is easy in our head. Just multiply, then mod by n at the end. Division. To divide, we actually multiply by the inverse. So we talk about the multiplicative inverse. The multiplicative inverse is the number that we multiply by such that we end up with 1. So in normal arithmetic, we said the multiplicative inverse of 3 is 1/3, because 3 times a third is 1. In modular arithmetic, the multiplicative inverse, actually we didn't have one here, the multiplicative inverse of 3, this was in mod 8, was also 3. 3 times 3 mod 8 gives us 1. Similar with subtraction. Subtraction, we add the additive inverse, the number that we add to it such that we get 0. Not every number has a multiplicative inverse. Every number has an additive inverse, but not necessarily a multiplicative inverse. And a number has a multiplicative inverse if it is relatively prime with the modulus n. So in these two sets, Z8, the modulus was 8. We mod everything by 8. We looked at all the numbers up until 8, 0 to 7, and found out which ones have a multiplicative inverse. 1, 3, 5, and 7. And if a number is relatively prime to the modulus, it will have an inverse. 1 and 8 are relatively prime. What does relatively prime mean? Greatest common divisor is 1. So relatively prime, greatest common divisor of the two numbers is 1. 3 and 8, relatively prime. 5 and 8, 7 and 8 are relatively prime. Therefore, they all have a multiplicative inverse. In Z10, mod 10, 1 and 10 are relatively prime. 1 and anything is relatively prime. The greatest common divisor of 1 and some other number will be 1. 3 and 10, greatest common divisor is 1. 7 and 10, 9 and 10, 1, 3, 7 and 9 are all relatively prime with 10. Therefore, they all have a multiplicative inverse in mod 10. The last thing we saw was that sometimes we can simplify some of the operations by taking advantage of the different laws of the arithmetic. And the last example we went through was if we can break a number into its divisors, we can simplify the calculation of the mod, or we can simplify multiplications by splitting it up into multiple smaller multiplications. When we have a large number, mod n, well, we can calculate that by breaking it into smaller numbers multiplied together, mod n. Taking a smaller number, modding by n, is easier than taking a large number. And some of the principles of those laws are used in algorithms that implement some of the ciphers we'll look at. The last thing we got to in the last lecture, again, relatively prime, greatest common divisor between the two numbers is 1. 4 and 1 are relatively prime. 4 and 2 are not relatively prime. 4 and 3 are. How many numbers are relatively prime with 4 that are less than 4? 2. 3 and 1 are less than 4 and relatively prime, so there are two numbers less than 4 relatively prime with it. We have a special name for this. The number of numbers less than n and relatively prime with n is called Euler's totient. And we use this symbol to say the totient of 4 equals 2. We calculated some others. The number of numbers less than 8 and relatively prime with 8, there were 4 numbers. So the totient of 8 is 4. So we had those two in the previous examples, and then we did a couple of others. as our numbers get larger, we need to check all the numbers less than n. As n gets larger, that becomes time consuming to check if it's relatively prime. But there are some shortcuts. There are some types of numbers where we can calculate the totient very quickly. If n is prime, the totient of a prime number, all numbers less than a prime number will be relatively prime with that number. So all numbers less than 13 will be relatively prime with 13. Therefore, the totient of 13 is 12. There are 12 numbers less than 13. 12 integers, I should say. The totient of a prime number is that prime number minus 1. So that's the shortcut. If we know we have a prime number, we can calculate its totient. If we don't have a prime number, we know it's not prime, it's composite, then we have to calculate manually. I think the lecture notes are not there. They'll be there at the break. Some are there, but they may be printing some, so they may run out. You can go get them now, or you can wait for the break. We're just going to do some more examples on the paper, so we're not referring to the slides just yet. The quotient of a prime number is the prime number minus 1. And another extension of that, if we know some number is made up from multiplying two prime numbers, 35, if we factor it into its primes, is 7 times 5. 7 and 5 are both primes. Then the totient of 7 times 5 is the same as the totient of 7 times by the totient of 5. And it's easy to show that. You can look at the reasons why the totient of a prime is p minus 1, and it follows. And the totient of a prime 7 is easy, 6. The totient of the prime 5 is easy, it's 4. Therefore, the totient of non-prime, of composite 35, is easy to calculate. It's 6 times 4, 24. So in fact, a totient of a prime number is easy to calculate, and the totient of a number which has two prime factors, or its two factors are both prime, is also easy to calculate. And that's a key principle or rule we'll use shortly. If we have a number n, and we know that it's made up of multiplying two primes together, we can easily calculate the totient of that number by calculating the totient of the two prime factors and multiplying them together. If we can't do that, then we need to go the long way. Try all numbers up to n. Try number 2, 3, 4, and check them all, and check if their greatest common divisor is 1. When n is large, calculating the totient is very slow. If n is large enough, you cannot calculate the totient within reasonable time. And that will be a security feature. Like brute force attacks, if we set the key large enough, we can't guess the key, we can't decrypt within reasonable time. Therefore, we consider a key of a particular length secure. We'll see that shortly, that if we have an n large enough, if the attacker is trying to calculate the totient of n, so long as n is large enough, and then they can't find the totient of n within reasonable time. So we'll get to that in a cipher. Let's give two equations, two theorems, and give a couple of examples of them, and then we'll return to our last two operations. So that's what we went through last week. And again, sorry you don't have the lecture notes in front of you, so we've covered these operations. What we're going to do, and I'll write them down again, is we're going to look at two theorems. We're not going to prove them, we're just going to use them. So I'll give the theorems to you, and we'll use them to solve some problems. The first one's Fermat's theorem, and the second one's Euler's theorem. Euler from Euler's totient function. And Fermat's theorem comes in two forms. Let's focus on the second form. So we can consider it, it's the same theorem but just stated in different ways. We'll just use the second form. If we have p as a prime number and a is some positive integer, then Fermat's theorem tells us that a to the power of p is the same as a when we're in mod p. That is, a to the power of p mod p equals a, as long as p is prime and a is a positive integer. Under the condition p is prime. We're not going to explain why that's the case. There's proof of that theorem. We're going to use it when we see some cryptographic algorithms. So what it tells us, as an example, what is 3 to the power of 5 mod 5? Easy, isn't it? You can calculate it the long way. You can calculate what is 3 to the power of 5 with your calculator and then mod by 5. Or you can see, well, this holds the form of Fermat's theorem. Some integer to the power of a prime, mod by that same prime, some integer a to the power of some prime, mod by that prime, is equal to a. So the answer is 3 there. I don't need my calculator to calculate 3 to the power of 5. And that's the idea. We can use Fermat's theorem if we have some statement in the form, we can quickly get the answer. We don't need to calculate. And that's again very useful when we have large numbers. One large number to the power of some other large number gives us what? Take one large number, hundreds of digits long, raise it to the power of another large number, hundreds of digits long. What's the answer? A very, very large number, because you raise to the power, then you multiply many, many times, and the answer gets very, very long. Long enough that your computer cannot calculate. But if we have it in the form of Fermat's theorem, we can find the answer from the theorem. We don't need to calculate it. What about another one? Can we check that? What is 3 to the power of 5? If with your calculator. Does anyone have a calculator? Right, let's calculate. Three to the power of 5. 243. 243 mod 5. 3. Okay, just confirm that 3 to the power of 5. We could calculate this because it's such a small number. So that one checks. Maybe calculate this one manually. Three to the power of 3 mod 3. 0. Does Fermat's theorem hold? This is a bit of a trick. It is 0, 3 to the power of 3, 27 mod 3, the remainder is 0. But still, Fermat's theorem holds because, in fact, when we do mod 3, 3 is the same as 0. So 3 equals 0 in mod 3 because 3 mod 3 is 0. So it does hold. When I have mod 3, I shouldn't be using numbers of 3 or more because 3 is the same as 0. Right? So just be careful that this is a trick in that, yes, Fermat theorems hold because 3 equals 0 in mod 3. So sometimes you'll come across this and you need to simplify. When you have mod n, get all the numbers to be less than n. Mod by n first. The other theorem. So we'll come back to that. We'll see it in play, but let's just give you the other one. Euler's theorem. And there are two forms again. So Euler's totient function, we know, it's the number of numbers less than n which are relatively prime with n, and there are some shortcuts. Euler's theorem has two forms. The second one we'll use. For positive integers a and n, if we have a, some integer, to the power of the totient of n plus 1, and we mod by n, we end up with a. So let's write it down and see it in some examples. We don't necessarily need primes there. A to the power of the totient of n plus 1, when we mod by n, gives us a. (97 to the power of 121 mod by 143). Try it on your calculator first. And then apply one of our theorems. Your phone has a calculator. A chance to use your phone during the lecture. 97 to the power of 121. Find out what it is and then mod by 143. (97 to the power of 121). We could calculate this the manual approach. And we get this long number. It doesn't even fit on my screen. Okay, that is 97 to the power of 121. And then we take that number and mod by 143. What do we expect to get? 97. Why is that? So that's the answer. Why do we know that without having to calculate the power? Well, let's check and see whether this matches Euler's theorem. So if we do it the manual way, we can do it and we find it's 97. But why is that? Well, Euler's theorem, some integer to the power of the totient of n plus 1. If we mod by n, we should get that integer a back. Does that work? What is the totient of 143? And here's a hint. 143 is not prime. Find the totient of 143. Shouldn't take long if you do it with a shortcut. It'll take long if you do it manually. You check, is 2 relatively prime with 143? Is 3 relatively prime with 143? If you go through up to 142, you'll spend a lot of time, well, 10, 15 minutes. But try a shortcut. Why? Right. Find the shortcut. That is, not having to try all 142 numbers. And some of the shortcuts, remember, the totient of a prime is the prime minus 1, but I'm telling you 143 is not prime, so that shortcut doesn't work. The other shortcut, the totient of a number which has 2 prime factors is equal to the totient of those 2 prime factors multiplied together. So the shortcut, find the 2 prime factors of 143. Find the factors of 143. Then you'll see. Something times something equals 143. What is something? What did you get? Something, one of the somethings is 11. 11 times 13 is 143. And the shortcut for Euler's totient function is if we know that there's just 2 primes multiplied together, then this is the totient of 11 times 13, and that simplifies to the totient of 11 times by the totient of 13. And now we can find the totient of these numbers because we know they're both primes. The totient of 11 is 10. The totient of 13 is 12. The totient of 143 is 120 because 143 has 2 prime factors. Its factors are both primes. Now we compare to Euler's theorem. Some integer, 97, to the power of the totient of our modulus, modulus 143, the totient of 143 is 120, plus 1. 97 to the power of 121, mod by 143, it matches Euler's theorem. So we can find the answer is immediately 97. So we don't need to calculate the power. We could in this case, the small numbers, 97 and 121. But with larger numbers, again, it would not be possible to calculate. So if it's the form of Euler's theorem, we can find the solution easily. So we're going to use this theorem, Euler's totient function, and some of our other modular arithmetic in a cryptographic algorithm in a moment. Any questions so far? In these, the use of the theorems, for example, in the exam, I'll give you them, or you'll remember the theorems, and you just need to know when to apply them. All right? So you may see some statement or some equation, and then you need to think, can I use one of the theorems to find the answer easily? And in this course, you'll usually have to use one of those two if there's similar structured questions. So we've gone through most of the principles of number theory. We've got one more concept to cover. Let's try. What operations have we done? We've done addition, subtraction. Subtraction is add the additive inverse. We've done multiplication and division. Division is multiply by the multiplicative inverse. What are the next two operations? Add, subtract, multiply, divide. Two more operations. To the power of, which we sometimes say exponentiation, the exponent. So some number to the power of some other number. It's called exponentiation. And what's the opposite operation? Not square root is a special case. Logarithm is the general case. Okay, logarithm takes us back and gets the original answer. So we need to do those, but with mod n in modular arithmetic. So we'll give a couple of examples. Exponentiation is easy. Easy in our brains at least. We just use the same concept as normal exponentiation. But let's just remind you before modular arithmetic. Ordinary arithmetic, just no modulus. Remind you, 2 to the power of 6. Everyone remembers their powers of 2 to the power. 64, because we deal in binary. So log in base 2 of 64 equals 6. So this is, we say, logarithm is the inverse operation of exponentiation. The base is 2, the exponent is 6, the answer is 64. If we take that answer 64, if we know the base is 2, then the exponent is 6. So that's our logarithm operation. Or the other way, if I know the log of 81 in base 3 is 4, then 3 is the base, 4 is the exponent, and the answer is 81. 3 to the power of 4 is 81. That's our normal arithmetic. We want to do those operations, but everything mod n, modular arithmetic. Three to the power of 2 mod 7. And similar with addition and multiplication, we can do that manually and just mod by 7 at the end. And we get 2. 9 mod 7, 2. So exponentiation is easy, at least conceptually, that we just calculate the exponent in the normal way and then mod the answer by our modulus 7 in this case. Easy conceptually. Of course, if we have large numbers, it may not be easy. A large number to the power of another large number gives us a very, very large number, and that may be hard to calculate and then mod. But we do know that we can simplify these using our properties of multiplication. We saw an example last week. We had 11 to the power of 7 mod by some number. We broke 11 to the power of 7 into 11 to the power of 4 times 11 to the power of 2 times 11 to the power of 1. So we can simplify the calculations. But exponentiation conceptually is easy. What about logarithms? Well, using the same concept, we would say the log, the base is 3. Now we added another number here. We don't have 3 numbers, we now have 4. We also have the modulus. And the way we write it is commonly 3, and there's another parameter here, 7, the modulus n. The logarithm with base 3 mod 7 of 2, the answer, equals the exponent 2. 3 is the base, 7 is the modulus, in the brackets 2 is the answer that we had from the previous operation, equals the exponent, what did we raise to the power of? 2. This is the logarithm. Well, we know that because we just did the exponentiation. We have a special name for this logarithm in mod n. It's often referred to as the discrete logarithm. So to avoid confusion, we'll often write d-log or discrete log. Discrete logarithm. The discrete log of 2 in base 3 with mod 7 equals 2. So that's how we write the logarithm. What is the discrete log in base 3 mod 7 of 6? Find the answer. Think about, from the exponentiation point of view, what does it mean, this question? What are we trying to find? What's your calculator say? 1. This is not a normal logarithm. You can't use the log button on your calculator because here it's a mod n. Right? So it's not the normal logarithm that we use on our calculator, and that's why we refer to it as something slightly different. We call it the discrete logarithm. Same concept, but everything is mod n. The discrete log of 6, base 3 mod 7. So what we need to think of, 3 to the power of something, mod by 7 gives us 6. Take 3 as the base, raise it to some power, and these are all integers, mod by 7, and the answer should be 6. 3 to the power of something, mod 7 equals 6. What is that something? 3 to the power of 3. 3 to the power of 3 is 27. 27 mod 7. Remainder is 6. So the something, the exponent, is 3 there. Therefore, the discrete log of 6 in base 3 mod 7 is 3. So that's how we think of discrete log. Any questions on logarithms? Yep.
So we are only dealing with...
Right, in our modular arithmetic, everything is from 1 up to n minus 1, where n is the modulus. Here in the example, n is 7, mod 7. The numbers we deal with are from 0 to 6, right, always. So, yes, it must be 3 to the power of some integer, mod 7, gives us 6. And these numbers should be all less than 7. Of course, if we have 10 here, it's the same because 10 equals 3 in mod 7. If we have a number larger than 7, we bring it back to the in the set 0 to 6. Don't use your calculator to solve a discrete logarithm. It won't work. Right? What about another number? We'll stick with small numbers so you can easily check them. Stay with mod 7. Discrete log, base 2, mod 7 of 4. Think about what the exponent should be. Think about the exponentiation operation. Something, 2 to the power of something, mod 7 equals 4. What is that something? 2? Anyone else with an answer? 5? Someone said 2, someone said 5. Let's check. So let's check from the exponentiation. Base is 2. 2 to the power of something, mod 7 equals 4. What if the something is, someone said 2? Correct? 2 to the power of 2 is 4, mod 7 is 4, okay. So the answer is 2. But someone else said 5. 2 to the power of something, mod 7 equals 4. Does 5 work? 2 to the power of 5 is 32. 32 mod 7 is also 4. Which one's correct? They are both correct according to our definition of 2 to the power of some integer mod 7 equals 4, where it could be 2 or 5. Both of them are less than 7. Okay, so that's okay. So we have two potential answers here. Now this is no good, especially when we use it in cryptography, and we'll say that the discrete log in base 2 or mod 7 of 4, we don't have a unique answer. We don't, or sometimes we say there is no answer. There's no single answer. So we'll often say that we don't want to have such a discrete log because we don't know what is the real answer. If we're using it as an inverse operation, And that's what we use in cryptography. We'll do an encrypt and decrypt. If one operation is the exponentiation, and you give me the number 4, and you tell me you used a base of 2 and mod 7, and I need to find out what exponent did you use, I don't know whether you used 2 or 5. So that's a problem, and we'll say for cryptography that there's no unique answer here, and we don't want to have such problems to solve in cryptography. If we want to find a discrete log, we want to make sure that there's always a unique answer. So the point is, only some values have unique answers. Not all values have unique answers. This had a unique answer of 2, this one had a unique answer of 3, but here we don't have a unique answer. The last thing, when do we have a unique answer? Under what cases do we get a unique answer? Well, let's consider in our mod 7, and let's consider the possible answers. Let's continue with mod 7. Some integer raised to the power of some exponent I, mod 7. Let's look at the answers. What are the possible exponents that are of interest to us? Exponent of 0 is not very interesting. Raise a number to the power of 0 and you always get 1. All right? Let's skip 0. So even to the power of 1 is not so hard either, but we'll write it down. Up to the power of 6. Because in mod 7, the numbers we deal with are from 0 to 6. If we get to 7, it's the same as 0. So let's write down, for different values of a, the answer of a to the power of 1 through to 6. Where a we'll write it in a matrix. Find the answers of a is 1, a to the power of 1, all mod 7. A is still 1, a squared mod 7. And we'll write the answers here. The first row is easy. When a is 1, 1 to the power of anything gives us 1. Mod by 7, we still end up with 1. So the answers here are 1 all the way through. So this is exponentiation, and then we'll see it when we return to the opposite discrete logarithm. If a is 2, 2 to the power of 1, mod 7, 2. 2 to the power of 2, mod 7, 4. 2 to the power of 3, mod 7, 2 to the power of 3 is 8, mod 7 is 1. 2 to the power of 4, mod 7. 2 to the power of 4 is 16, mod 7 gives us 2. Fill it in for the rest. Take you 2 minutes. You can use your calculator if you like. And for the next rows, just let's fill them all in, and then we'll see how it relates to discrete logarithm. 2 to the power of 5 is 32, mod 7, 4. 2 to the power of 6, 64. Mod 7, 9 sevens is 63, gives us 1. Now the power's 3 to the power. The first one's easy. 3 squared, 9. Mod 7 is 2. 3 cubed is 27. Mod 7, 6. I'll give you a chance to fill in the rest. It's all right, you're allowed to have the calculator in an exam. Not your phone, but a calculator. Make sure you have a calculator in the next 2 weeks. Can someone tell me the answers so I don't have to calculate? 3 to the power of 4. Mod 7. 4. 3 to the power of 5, mod 7. 5. 3 to the power of 6, mod 7. Now, powers of 4. 4 to the power of 1 is 4. 4 squared, 16. Mod 7 is 2. 4 cubed. Let's bring up the calculator. What do we got? 4 to the power of 3, mod 7. 4 to the power of 4, mod 7. 4 to the power of 5, mod 7. 4 to the power of 6, mod 7. 1, 4, 2, 1 to finish off that row. And while we're here, 5, all right, let's go through them all. Five to the power of 3, mod 7. So with 5, the answers are 5, 4, 6, 2, 3, 1. You write them down, I'll do the rest. Six to the power of 1 through to 6. With 6, the answers are 6, 1, 6, 1, 6, 1. Okay. So I did them for you. Write down the values, good. And have a look at the patterns. For different values of A, when do you get unique answers? Let me write them down. That is, with mod 7, with all possible values of A, we raise to the power and then mod by 7. These are the answers. Why do we do this? We want to know when do we have a unique discrete logarithm. The opposite, remember, is the discrete log. discrete log in the base A mod 7 of some number, let's say equals x, of some number x equals our exponent I. We can calculate the exponentiation, all right? We can calculate those values. But when can we find a unique answer for the discrete logarithm? Well, let's look up our table. If A is, let's take an interesting number, A is 2. So the second row here, if A is 2, if the answer is 4, what's the exponent? If x is 4, the discrete log base 2 mod 7, what's the index I? Base 2, the answer is 4. The index is either 2 or 5. We don't have a unique answer there. We don't want this case. In cryptography, when we apply the discrete logarithm, we want a unique answer. Here we don't know which is the answer. What if the base was 3? A is 3. Discrete log base 3 mod 7, so the third row. If our answer x was 6, what's the index or the exponent I? Well, there's only one value of 6 here, so it must be 3. The discrete log of 6 is 3. If the discrete log of 5 we know is 5. The discrete log of 2 is 2. Because when the base is 3, we note that these 6 values are distinct. There's no repetition. And you should see that in that table. You see the pattern. Some of them repeat. This number repeats. 2, 4, 1. Repeat. With 3 of those 6 answers, they're all different. And that's what we need if we want to be able to find a unique discrete logarithm. If we have repetition, then it could be one of multiple answers. With 4, we have repetitions. You see here, it's 4, 2, 1, 4, 2, 1. With 6, it's 6, 1, 6, 1. With 5, we have distinct values. When we want to have the discrete log with mod 7, we'll only use a base of 3 or 5. Because only those 2 bases will give us a unique answer. The other bases of 1, 2, 4 and 6 will give us non-unique answers. And if we don't have an answer which is unique, we don't know which is the correct one. And we'll see that's not useful when we apply cryptography. Because what we're going to do is use exponentiation as one operation, like encrypt, discrete logarithm to decrypt. And we need to get the correct answer. So, 3 and 5 are the only bases that we can use there. What we say is that there's a name for those. 3 and 5 are primitive roots of 7. Three and 5 are primitive roots of 7, meaning for all the numbers up until 7, 0 up to, or here we cover 1 up to 6, that are greater than 0, we raise those 3 to all those powers and you'll get a distinct set of answers. That's what the definition of a primitive root here. Or, if we want to find a unique discrete logarithm in mod n, the base must be a primitive root of n. Discrete log of 6, base 3 is, we can simply look it up in the table. Discrete log of 6, base 3 is 3. The answer is 6. What index, what exponent gives us the answer of 6 in base 3? A to the 3 gives us 6. The exponent is 3. So we can't find discrete logarithms of any number. We can only find unique answers for when we have primitive roots as the base. The last thing to say, finding discrete logarithms is hard. When we have large numbers, it takes a long time to find the answer. So unless we have some shortcuts, a long time, if the numbers are large enough, you'll never find the answer of a discrete logarithm. There are no known algorithms that would do it in reasonable time. And that will be used as a security feature. Questions on discrete logarithms? Yep.
So every time you do it, you kind of have to apply this logic of mathematical rules, or do the machines
Right.
calculate
So how does our computer calculate this? There are algorithms that will try to simplify, to find the discrete logarithms. So in the same way that there are algorithms to find prime numbers, different algorithms. Same for defining discrete logarithms. There are algorithms faster than what we did here. Okay, but when the numbers are large enough, they still will take forever in practical time to find the answer. Okay, so there's no fast algorithms.
algorithm, not like we punch in the calculator 3 times 5.
Well, when you punch in the... exponentiation, we see it's quite simple. It's similar to our normal arithmetic. So the way that your computer does exponentiation, raised to the power. But again, there are algorithms to speed it up. The exponentiation, we saw, was it 11 to the power of 7? Rather than calculating that directly, we can break it into 11 to the power of 4 times 11 to the power of 2 times 11 to the power of 1. That's one of the algorithms for speeding up the calculation. So there are ways to speed up the calculation, yes. And your computer will implement them. But for discrete logarithm, there are ways to speed it up, but no way to make it solvable with very large numbers. So many people may have the lecture notes now, but let's just summarise what we've done. We've gone through a number of examples today. Fermat's theorem, the second form we've looked at, and that's what we'll use. Euler's totient function, the number of numbers less than n relative to prime with n. Euler's theorem, remember it or use it. We'll see some examples. Logarithms, we refer to as discrete logarithms. So that defines what we just did in those examples. The discrete log, base A, prime P, mod P of number B, the index, the exponent is I. So we've seen discrete logarithms. And we can only find an answer, a unique answer with a discrete log when we have primitive roots. And it's more than the case we considered when P, the modulus, is prime. We used mod 7, 7 is prime. Then we can find unique answers if the base A is a primitive root of that prime P. All raised to the powers and we get unique answers. This is for mod 19. Prime p of equal to 19, similar to what we did, but with the textbook gives a picture of the primitive roots of 19 are, if you look closely, at 2, 3, 10, 13, 14 and 15. All the numbers, when we raise to the power of 1 through to 18, give us a unique set of answers. There's no repetition in the answers. And we can use that to find the discrete logarithm, so that's just a lookup. That grabs those 6 rows from that table. And to finish, we've mentioned along the way, but we'll summarise, some of the problems that we've come across, we say are very hard to solve. We define as computationally hard in that if we have inputs large enough, there are no known algorithms that can solve them in reasonable time. Your computer cannot find the answer if the numbers are large enough. And the 3 problems, which are about equivalent in complexity, integer factorization, which is, and we'll see it for our security, given some number n, we know n was made up of multiplying 2 primes together, p and q. I give you n, find p and q. If n is large enough, you will not be able to find p and q. That's the problem there. Where p and q are primes, find them, well, that's considered, there are no known algorithms that will do it within reasonable time. How large is large? Some examples, maybe these are a bit old now, but the 2 primes were 768 bits, or about 200 decimal digits. So you write down a prime number 200 digits long, and another prime number 200 digits long, multiply them together and you get a much bigger number, n. I give you n, you will not be able to find those 2 primes p and q. The other thing that's hard to calculate, Euler's totient. Given n, I give you n, find the totient of n. Assuming n's not prime, it's composite, find the totient of n, and that's considered hard to solve if n is large enough. Harder than solving factorization, in fact. We'll see that in one of the algorithms we'll come across where n is equal to 2 primes multiplied together, it's easy to calculate the totient of n if you know p and q. We have a shortcut. But it's hard to find the totient of n if you don't know p and q because there's no known algorithms. That will be a security feature. And discrete logarithms are hard to find the answer to. Given the modulus p, the base a, and the answer b, find the exponent I, it takes a long time to solve that. Right? So these are 3 problems, and it will be easy to calculate n, or the totient of n, if we know p and q, but if you don't know p and q, find those values, we'll see that they're not solvable, and that will be a security feature of the algorithm called RSA. Let's finish with one or a couple of examples that you can finish over the break. Just to remind you, we'll quickly solve these. No calculator required. Maybe in the last one. For questions taken from past quizzes or exams where you need to solve, the last one I think a calculator was allowed, the first three no calculator allowed. The idea is to think about the shortcuts, not to solve them manually, but to think about how can I get the answer to the totient of 23 quickly? Is there some characteristic of 23 that makes it easy to calculate? Is there? What's the answer here? Why is it 22? 23 is prime. So the shortcut is, if we have the totient of a prime number, the answer is that prime number minus 1. There are 22 numbers less than 23 which are relatively prime with 23. So there's the shortcut. We recognise 23 as prime. Next one. What shortcut are you going to use? No calculator. Well, the hint, we've introduced two theorems, Fermat's theorem and Euler's theorem. One of those. See if it matches one of those. And I've created it such that it should. Discrete logarithm, base 2, mod 19, that's a 9 there, of 3. Well, if you look at your slides, and if you don't have them, I'll show it up. You can look up that value. The discrete logarithm is actually on one of the slides. Sorry if you don't have it. Log base 2 mod 19 of a. The answer is 3. Where is 3? The exponent should be also here, 3, 13, this one's better. The other one's back to front. Similar to the table we drew, 2 to the power of 13 mod 19 equals 3. Therefore, the discrete log of 3 in base 2 mod 19 equals 13. So that one requires a lookup table because we take time to solve it ourselves.